Hello! Hello, everybody. Welcome to the LIUniverse. I'm so glad you're here with us. I'm Dr. Charles Liu, your host, but please, if you possibly feel good about it, call me Chuck. I am happy to be here today, as always, with our wonderful co host, Allen Liu. Hey, Allen, how's it going?
Hi, it's going pretty well.
Okay, seen any good webcomics lately?
Oof, I mean, there's always the classics. You got your XKCDs going
Oh, yeah.
on. You got your
Oh, yeah.
Saturday morning breakfast cereal.
Oh,
I don't know,
okay.
hashtag not an ad.
Good, good, good. Glad that they're holding up their end of the quality spectrum. And our special guest today, I'm so happy to introduce to you all Dr. Isabel Colman. Hello, Isabel. Good to see you.
Hi, good to see you too.
Hey, thanks so much for being here with us. You are at the American
Yeah.
Museum of Natural History. What is your position there, basically?
I'm a postdoctoral fellow, which
Okay,
is basically like an early career
terrific. So
research job.
after your doctorate, your PhD, hence Dr.
Yeah.
Coleman, you are now at the next level and doing work,
Yes.
as I understand it, on things that have to do with stars and how they spin, right?
Yeah, that's right. So do you want me to give a brief summary of my work?
Sure.
Oh, no, it's just really quick. Like I study stars, but and I'm looking for stellar rotation, but I do it from a kind of data science perspective,
Oh, okay.
in that I'm looking at large volumes of data from the TESS telescope.
Yes, yes. That transit exoplanet explorer thing. Yes, definitely
And
tell us.
you can't look at planets without looking at stars first.
Oh, that's
That's what we
true.
would always say.
That's a great point. Okay, so we'll get to that in just a few moments for sure. But right now, yes, it is our time to share and discuss today's joyfully cool cosmic thing. And as it
That's
turns
the
out,
order.
I got it right this time. Okay.
Yeah.
Well, it turns out that the cool thing that I saw recently is that there is apparently a comet in the sky, which is, happens all the time. So that's cool as it is. But what's neat about it is this comet is green. In other words, if we had sensitive enough eyes to take a look at this comet and really capture its colors from us, it's green colored. Now, normally it's not green color. So this is kind of cool. And when I saw this, it immediately reminded me of the old song that we used to sing in elementary school. Anybody know what I'm talking about? About comets and green stuff? No? Oh, man.
I'm from another country, so
I'm from another
not at all.
generation,
I
so
know, I know. Okay, it goes like this. Comet, it makes your mouth turn green. Comet, it smells like gasoline. No?
what?
All
No,
right.
it's a
Never.
common cleanser.
Yes, Comet Cleanser. Um,
Oh
and
man.
and the you guys recognize the tune that I just hummed?
Yeah.
That's from the Bridge on the River Kwai, right? And that's a movie from a long, long time ago. Yes. And so it goes on there that so we children just of that era turn the comet, makes your mouth turn green. Comet smells like gasoline. Comet, it makes you vomit. So get some comet and vomit today. Things like that. Anyway,
Also not an ad.
but hardly cosmic. But this is a green comet, which is really cool. And if we're lucky, we'll see what it looks like. Now, Isabel, what makes comets green? I mean, what makes comets colors in general? I, as many of you know, I'm a galaxies guy, so I know what makes galaxies look green. But what makes a comet look green?
Well, what makes anything look any color is basically the wavelength at which it's emitting light.
Okay.
Um, and
Mhm.
in this case, it's emitting light at particular wavelengths, which reach our telescopes at particular wavelengths, based on a carbon-carbon reaction.
Oh,
Oh,
okay.
So
cool.
yeah,
So
so
wait,
it's just the
you
composition basically.
Okay, so you have lots of carbon in this comet compared to other comets, and then
Yeah.
somehow they interact with one another in a way that's unusual compared to other comets. And therefore, when light bounces off of them, it comes off as a greenish hue.
Yeah, when it's a refraction process. It's the same thing that happens in our atmosphere,
Oh,
but kind of
in
So
on
reverse.
a
like
different
say
Yeah.
scale.
so how sky is blue because of the oxygen and the Rayleigh
Yeah,
scattering and stuff.
exactly. It's a
Oh,
similar
super
process to
cool.
that.
That's really neat. Okay, I'm glad to hear that. Okay, so that's just fun. Anyway, I just thought it was really a
Yeah.
cosmically cool thing to do, and I want to talk colors with you a little bit later because I understand, that when it comes to doing stars and just photography and measurement of things like that in general, color is such an important way in understanding what we're doing and how we're doing it.
Yeah, for
So,
sure.
yeah, well, right now would be a good time for a question from an audience member. Alan, do we have a question from somebody that would be good for Isabel to answer?
Yeah, we've got a couple questions. We'll start with a question from a student. This is a student named Thomas. And this question is, what would happen if our sun collided with another star? So that would really affect its
Ooh.
rotation, at least, that's for sure.
Yeah, I mean, well, when we're talking about rotation, the first thing I always think of is the angular momentum transfer, right?
Okay.
Um, so like I'm sure a lot of people from like watching The Martian, right? You'll be familiar with the slingshot effect,
Right.
where they use the transfer of angular momentum between two bodies to make one body go faster. So the same kind of thing would happen if like I mean, it does happen in binary star systems, right?
Mhm.
Okay.
Stars do collide.
Wow.
Our sun isn't a binary, but say you had a binary where one of them was evolving at a faster rate than the
Okay.
other, so it's getting bigger faster, and they're spinning around each other. There's some sort of angular momentum transfer going on, and eventually they combine.
Wow. So they would
Wow.
all
Yeah,
come together, be like two stars would become one. But during that
yeah.
process, there's a lot of spinning and weird stuff going on.
Yeah, and to be honest, this is one of the like least understood things in astronomy. There's something called the common envelope phase,
Oh.
which is where you have the two stellar cores inside the same convective envelope.
Oh, neat.
So it's
Oh, so like
before
the
they,
centers of the star, they're still separate, even though the outer
yeah,
layers of the star are merged already. Wow.
right, yeah, it's really cool. And like I've studied a little bit, but like one kind of obviously it's really hard to observe, and we're not
Yeah,
quite like it's
because you
hard
can't
to
see through a
know.
star.
Exactly. It's hard to know if you're looking at stars in their common envelope phase.
Okay.
But there's a lot of people doing really good work on modeling it.
Terrific.
Wow.
Wow.
Yeah.
So that was a much more complicated answer to a simple question than we thought. Thank you, Thomas. That's great. I think that's wonderful. So,
Yeah.
um, tell us a little bit about what happens when stars spin, Isabel. Your research, I mean,
Yeah.
we know that our sun, for example, spins around. It spins around on average about once a month, right?
Mm.
And because it's kind of a ball of hot plasma, some parts of it spin faster than others. But I
Yes.
mean, aside from seeing sunspots once in a while, we don't really detect or sense a lot of influence of that on our world. But you're looking at things that are more extreme or things that might
Well,
affect things a little bit better, more significantly.
not quite, but I do want to say it's really interesting that you mentioned star spots because that's actually what I'm looking for.
Oh,
Oh.
Yeah. So like a lot of younger stars and cooler stars are really good targets for looking for spots because
Okay.
especially like M dwarfs, which is a really sort of color, really red and small stars,
hmm
Hmm.
they have a lot of magnetic activity. But all stars, I mean, we know the sun has magnetic activity, obviously, because we can see spots on its surface.
Yeah.
So plenty of stars will have these like regions of intense magnetic activity, um, which leads to just a region of lower temperature, or
hmm
like you can think of that as well as lower emission. So the color is actually darker, and that's how we detect them. Because if a
Oh,
star is rotating, it's like you know how people look for exoplanets by looking for the dip when the planet goes in front of the star. It's
hmm
pretty much the exact same method, but it looks kind of different because you've got like a spot going in and out of view on the surface.
oh,
Oh.
cool. So can you actually sense it just by looking at a star to see how it bright, dim, the pattern that it
Yeah.
changes that way? Okay.
Yeah, so you have to observe the star over time, which is what
Hmm.
telescopes like TESS do.
Because they're
You
looking
get
for those exoplanets.
exactly. This is like something we always say is you can't study planets without studying stars first. And there's
Right.
like a
Mhm.
huge community around doing stellar astrophysics with TESS.
Wow.
Wow.
Um, and so yeah, we're looking for these changes in brightness, same as you do for exoplanets, but like a different pattern.
Mhm.
And
Okay.
it's really all about like finding that distinct pattern and being able to say, that's rotating
Ah, when
Wow.
because
you
we can see a
yeah,
spot moving.
it's really cool. When you talk about patterns in stars, I think about like the patterns on of our sun, for example, that occur because there's nuclear fusion in the center. It's like back when I was a student, right? The Gong project was started. Gong,
Mm.
it's seismology on the sun, because watching the sun, it's like if the sun is being struck by a gong, right? It's being
Yeah,
struck, and
Wow.
so it rings, and you can actually,
it's acoustic.
depending on the kind of telescope you use, you can actually see the vibrational waves coming out of it. So
Wow.
yeah, we call that stellar or helioseismology, right? Now you do that too, the stellar
Yeah.
seismology, the same kind of thing, looking at patterns of bright and dark.
Yeah, so where I actually started was in an astroseismology research group at the University of Sydney.
Oh,
Okay.
So astroseismology is actually a pretty recent field, like the last sort of 30, 40 years. And it's doing the same things that you've described for the sun, but observing that in all sorts of stars.
wow.
Wow.
Can it actually be
How?
done? I mean, yeah, Alan, go ahead.
Yeah, I was gonna say how like the stars are just so much farther away than our sun. Like, how would you even know that they're ringing?
So you need a lot of data. Um,
Yeah,
so
sounds like
Ke-
it.
um, the Kepler telescope, which is the predecessor to TESS, really opened this up. But also the Kourou satellite, which was a
Oh yeah.
ESA mission. Um, they basically just I like to. Well, I'm most familiar with Kepler. So what Kepler did was it just looked at one patch of the sky for 4 years,
Mm.
and that's a
Mhm.
lot of data, right?
Yeah.
Wow.
Um, so you're looking for repeating patterns, and when you can we use a lot of like pattern finding algorithms like Fourier transforms, and it's like the more data you have, the more likely you are to find these oscillations.
Okay. So
And
go ahead.
yeah, I was going to say, red giant stars are actually one of the most useful types for this. I mean, there's a whole bunch of them, but a red giant is basically the sun, but bigger. So
Oh,
if you think of the
Okay.
sun as like an oscillating three-dimensional body,
mhm.
then like it's like with a musical instrument. When you make that bigger, the frequencies get lower.
Hmm.
Oh.
So
Super
you can
cool.
actually, yeah, you can actually observe those depending on like the time cadence that you use to observe them. It's
Mhm.
actually easier
Mhm.
to observe lower frequency oscillations.
Oh,
So
wow.
there's been a huge amount of red giant science done that
Oh,
way.
I see.
Yeah.
So for example, what you're saying is that whereas a violin is very small, if you blew the violin up in size to like a cello or a double bass, you can actually see the vibrations more effectively with a
Exactly.
telescope
Yeah.
set. That's just amazing. That's super cool. Very musical, actually. I mean,
Yeah.
as you all know, the music of the spheres is something that Kepler thought about a long time ago, hundreds of years ago, and there's lots of music stuff. But a lot of us,
Yeah.
astronomers are very musically inclined. So I bet you are too.
Yeah, yeah. I've actually been a singing in choirs my whole life, pretty
Ooh,
much.
oh,
That's
cool.
great.
So
Oh, tell us about
yeah.
it. What kinds of choirs? Like big choirs, little
um,
choirs?
I've done it all. Like mostly I would say I've sung in chamber choirs, but I've
Mhm.
also had experience doing like symphonic chorus,
Ooh,
a couple of staged operas. So not like being an actual opera
uh-huh.
chorus, but
Oh no, that's
same
great.
kind of
Oh,
feel.
oh, that's fantastic. We are so glad that you have that and bring that music to the science. I'm sure it's just makes it nice, right? Because
Yeah,
you've been doing music even longer than you've been doing science, right? I mean, you probably didn't start
absolutely.
science until you were like an adult or something.
Yeah, I mean, I was definitely always interested in doing science as like I just like liked learning about it at
Oh,
school and like
okay.
in high school I was in an astronomy club.
Oh, okay.
So I was
So
kind of
you were
yeah.
as much an astronomer as a child, as a young person, as you were a musician. It's like this is all tied in together. Your
Yeah.
identity is like all these things together, right? That's
That's
cool.
actually really funny because it was like what I was at high school. I was the choir captain and I was the president of the astronomy club. So
There
those
you
were
go.
my things.
That's
That's awesome.
awesome. No, that's great that we have that kind of background stuff. Do you do other stuff that's highly artistic as well? I imagine,
Um,
we have a lot of audience members who are like, oh, I have to be either an artist or either a musician or either a scientist,
Yeah.
and that's not it
No, you
at
don't.
all, right?
Yeah, I've been learning darkroom photography recently. So like
That's really
Oh,
cool.
processing my own film and developing my own prints.
really?
That's been pretty
So
great.
like chemicals, like
Yeah.
actual stuff that's like built. Wow, wow.
Yeah, like with you put you actually get your roll of film into a tank and pour chemicals into it.
Amazing.
Um, and then you
Wow.
have like trays full of chemicals for prints. It's pretty fun.
You
That
do
sounds
like
really cool.
that sounds cool. Is it color photography or black and white photography or
Black and white.
wow.
Yeah, which is not like something I ever did before like 2 months ago. I had like no interest in black and white photography, but I'm like I've just been getting so into it.
So Isabel, do you have any of your cool film photography chemical based stuff that you've done that maybe you can show us?
Yeah, here's one I prepared earlier.
Okay.
Um,
Oh my
this
gosh.
is this is the cloisters.
Whoa.
Oh,
Now,
So I
some
live in Uptown Manhattan.
uh-huh.
So
Some of our audience members don't have the video; they just have the audio. So you can describe it to them, kind of like voice style. It's like a door,
okay, yeah.
but the door is like illuminated on either side, and then there's something kind of vaguely wheel-like on the right side. Wait, tell us about this.
So,
This is so cool.
so there's a couple arches here, but the arches of light you can see is the light that's coming through the arches of the cloister.
Wow.
oh,
Um, and that's just some stone walls of the building. That's a door.
So the
And
dark
this
part
really
is
bright
ironically
area
the
is like a
door,
window.
right? Ironically,
Yeah,
that
the
the
dark.
yeah.
Yeah.
That's super neat. And it's
it's a
so
cool interplay
artistic.
of light and dark there.
Right,
Yeah.
right. You see the shadows and so forth. And if I were really conspiratorial, I would imagine that those arches of light are actually weird, ghostly creatures that are walking around in the light as the dark and they're sliding back and forth. That's just so neat. You have that sense of like you want to play with light and dark and how these things slide back and forth. Is that the gist
Yeah.
of that work?
For sure. And like so this was for an assignment for my class actually, where we had to look for beautiful light.
Oh.
And
Oh,
so so like to some extent you're choosing it with the camera, but then when you get to the darkroom and you get to printing it, you also get to make decisions that will change how the final product looks. Like
huh.
we were talking a bit about filters earlier with James Webb.
Yeah.
Yeah.
With photography, you can, when you're printing photos, you can use different filters to change the contrast. So this is like this is a 3.5 for any nerds out there, photography nerds. It's a 3.5 filter, so that kind of increases the contrast.
I see. Wow.
Yeah,
Now, what this is triggering in my mind is to think that if you can do that with the photographs you're taking of, say, the cloisters or other places that are terrestrial, and thus you're putting in filters and changing contrasts and things like that, you could do that for astronomical data too, right? So you could imagine someone taking pictures from a telescope, it coming down, and then processing it in such a way to add or subtract things that you otherwise wouldn't see. Am I on track here? Is that the right thing? That, like, for example,
yeah.
do you do that for the data that you're doing for tests and so forth?
I have worked with something called image subtraction,
Ooh.
which is kind of like a contrast increasing exercise, which like I spoke about how I'm really interested in variable stars,
Hmm.
which it's a broad term that just means anything that's brightness changes over time. But
Yeah.
one way you can really emphasize that when processing the images is, so you have like all your images at different timestamps, and you take an average of those,
Ah.
and then you subtract the average from every timestamp. So what you're
Oh,
doing is you're getting rid of whatever stays the same and leaving
Ah.
only the stuff that changes behind. So you can think of that like really increasing the contrast on it.
that's really
Absolutely.
cool.
Wow. Yeah, and amongst galaxy folks, a number of years ago, there was a astronomer named David Malin an Australian who used photographic plates, pictures of stuff, to reveal
Mm.
extreme details that otherwise would be washed out by light. He used this a technique called unsharp masking, which was really cool. And I think you can
That's
do it
cool. Yeah.
digitally, but he did it with film, and
Wow.
that was a really neat thing. You know, things that nowadays we try to do with our computers, but back then, if you actually like take a camera and take a light box and work things back and forth, and you get this. So really what you're doing in your darkroom is enhancing your skills or your eye for the science that you're doing on your computer, right?
Yeah, I mean, in a way, it's all kind of related. Like, I'm also, I'm the same age as the internet, so I kind of grew up in the generation that was playing with like Photoshop, but even before that, there was like Paint and Apple Paint. I used to play on
Yeah.
one of the family, like my grandmother's computer. I would go in and like change the little pixels and to
Oh,
That's
like make
always
an
fun.
image look different. You know, it's all like it's just like I'm from the generation of images, so all this work is connected in a way.
fantastic. Yeah, let's see if we have another question. Alan, is there another question for Isabel that we have from the
We
audience?
do have a second question. This comes from our Patreon patron Cameron.
Hey, Cameron,
and this
thanks for being a Patreon patron. Yay! Yay, Cameron!
Yeah,
We love our
awesome.
patrons. Woo!
We do love
Oh,
our
sorry.
patrons on Patreon.
Sorry for the interruption. Please continue. Please
Yeah,
continue.
this goes a little bit into exoplanets and the kind of stuff that Tess is doing. So this is saying, so Cameron's question is this: fire is incredibly rare in the universe. You need to have an atmosphere rich in oxygen for rapid oxidation to occur. So, would the lack of ability to produce fire prevent intelligent life from forming?
That's interesting because fire and intelligence is one of our foundational myths, right? Prometheus gave fire to humans,
And that's how we
and from
became
that they
civilized,
developed
right?
culture.
Yeah.
Yeah, but I'm not sure it's so like clear cut scientifically speaking.
Mm-hmm.
Because I mean, the other thing I was thinking is that like there is life in the oceans.
Yeah.
Where there is no fire.
There is no fire.
Except in like
So-
parts of Lake Erie back 40 or 50 years ago. Because
Well,
of
that's on the
pollution.
surface.
Sorry.
like oil spills.
Yeah. That's a great point, Isabel. So actually for them, fire is not necessary. Is that what your point is?
I
So,
don't
like-
really know enough about like how ocean life evolved because I made a point of not taking biology as far as I could at school.
That's fair.
But
Well, because I'm thinking of like some intelligent, some ocean life that we think of as very smart, like whales and dolphins, are descended from land life forms. But then
Yeah.
others, like octopus, they're not descended from land life forms, and they also seem pretty smart in terms of their ability to solve puzzles and do things like that.
yeah, I guess it depends how you define intelligence.
Yeah, and the other thing that I was thinking about this is that a lot of the diversity of life that we have is possible because of oxygen, because it gives us so much chemical energy to work with. So there are plenty of organisms that don't need oxygen, but they're usually like very simple organisms or stuff like plants. Even things like mushrooms need oxygen. So like maybe it's possible that something like a plant intelligence could evolve on a planet where it wasn't powered by oxygen, where it was just powered by photosynthesis or something, but then maybe oxygen makes it easier for there to be more kinds of species and thus be more chance that one of them will become an intelligent civilization.
I mean, the question asker pinpointed it, right? That fire has been so essential to the development of so much life above water on Earth.
Yeah.
That it would be hard to get that. I mean, there's no evidence that there's ever been fire on Mars, right?
Yeah.
I guess there's been lava on Mars, though.
Yeah.
It's a little different, but yeah.
But it's, sometimes lava sets things on fire. That's how my brain was working, but I don't think it could have happened in the Martian atmosphere, right?
I think you're right.
And then you think of places like Titan, right, where they have, the lakes are made of methane and hydrocarbons. And so maybe for them, a fuel resource would be an oxidizer instead of a combustion.
That's right. Except that,
object
remember,
like carbons.
we still don't know whether there's life that's any other form other than our carbon-based stuff. So that's wild
That's true.
speculation. That's
It
fun
is
to
Yeah.
wild
think about.
speculation.
No, but
Wild speculation is always fun. But
Cameron, you have brought up an excellent point. Thank you so much for your question, and thank you for your patronage on Patreon of this great show. Well, wait, I shouldn't say it's great because I'm just on the show. Other people can
I
say
think
it's
it's great, but
Oh.
Yeah,
I'm
it's
also
great.
on.
We're just having fun here. Thank you. So, Isabel, do you feel like the work you do in astronomy is more like tedious coding stuff or more like a video game where you're really playing with computers like it's a toy?
I think it's not fair to call coding tedious. I think coding is a really creative art.
Okay.
I don't personally play video games, so I can't really like jump into that comparison.
Mhm.
But I think coding like it has a bad rep for being boring because often you have to do a lot of debugging, which can be really boring.
Yeah.
But like the actual process of building an algorithm and
Mhm.
putting together code from scratch is a creative process.
Wow.
It's
Yeah.
not, I'm not just doing it by rote. I'm actually feel like often to create an algorithm, people are drawing diagrams
Right.
to like work out what happens. It's like tangible.
That's
So,
great.
so it's
Yeah.
really creative. You really feel like it's almost artistic in a sense, or at least if you imagine, say, someone trying to design a new airplane or trying to design a new car or something like that. Yes, there's technical aspects, but there's also artistic and creative aspects, even to code. Then,
Yeah, I think to make the kind of decisions that science requires, I don't know if there's I don't the more I do, the less I believe that there's like some kind of boundary between technical skill and creative skill because it's all just like thinking in new ways.
Wow.
cool.
That's a good way of putting it.
Yeah.
Yeah.
So you do consider yourself a data scientist of the stars, but at the same
Yes, for
time, you're
sure.
also an artist of the stars, a creator
Yeah, why not?
who appreciates the music of the spheres, so to speak.
Maybe an
Yeah,
artisan too.
absolutely. I am a big fan, top streamer on Spotify. um,
Well,
I
wonderful.
just think that you know, data science, a lot of people are like, oh, you're just crunching numbers. That's so boring. No, it's not.
It's
Like,
not.
it's
Numbers
fun.
are great. As the math person, numbers are great.
That's right.
Thank you.
That's
Yeah.
right. Oh, that's great. Well, that's wonderful. Isabel, the time has flown by. We've had so much to talk about, but we still have so much more to talk about. Thank you for being with us on this
Yeah,
episode. I
my
hope we can
pleasure.
talk to you again sometime. Thank you so much. If we want to find you, is there any easy way that our audience members can find you on social media or internet or anything like that?
Yeah, I'm not on social media, but I have a website where you can read about the work I do and contact me,
Okay.
and that is just ilc.fyi.
Oh,
How
it's a nice little
convenient.
short URL there.
Yeah, nice and
ilc.fyi.
simple.
Terrific. We will absolutely go find you there. And I want to
Great.
thank you again so much, Isabel. Dr. Isabel Colman at the American Museum of Natural History. Thank you for joining us today. We hope to talk to you again very, very soon.
Thanks for having me.
Yes. Alan, as always, our co host, thank you so much for being here. Thanks for doing what you did today.
Yeah. Thanks for you doing what you did.
Thanks. And to everybody out there in the audience, thank you for being part of our episode today. If you liked what you've seen and heard today, please feel free to support us on Patreon. And as always, thank you for being a part of the LIUniverse.